Hello and welcome to this month's edition of Office Hours by Bick Gardner. My name is John Kowalski. I'm part of the marketing team here. I'd like to welcome you. Today, our speaker, Mr. Noah Morgan, is our applications specialist, and he's going to be speaking about color measurement tools and uses. If you're unfamiliar with our office hours format, it's a shortened presentation that is usually 20-25 minutes long, and then it's open discussion followed by your questions, comments, any challenges at your own facilities. We're here to help. We are also recording this, so immediately following the presentation, you'll receive an automated link with the presentation, as well as the discussion that you can, take a listen, later this week, next week, share with colleagues, whatever you like. So if you have a question, please log it in the chat box located in the bottom right-hand corner of your screen, and we'll get right to it. Noah, how are you, sir?
I'm good. Thank you for asking. So thank you for that wonderful introduction.
You bet.
Like you mentioned before, today we'll be talking about color measurement tools and their uses.
Yes, sir.
So without further ado, I'll start it off. So starting off, this is our Spectre 2 guide. This is one of our new handheld color instruments. We see these are some of its specs on the right side there. So there's two options available. You can get it in either the D8 spin and specs geometry or the 45-0 geometry. If you're unfamiliar with those mean, we'll touch later on those, what they actually measure further in this presentation. We also see that the illumination or the illuminated area, so your sample measurement port at the bottom of the instrument is 12 millimeters, but it actually measures an area of 8 millimeters. Further down, we see that it measures in 60-degree gloss with a measurement area of 10 millimeters by 5 millimeters. So to start off and really understand the difference between those two different versions I mentioned, so that D8 spin and specs, or SPI and SPE, and that 45-0 geometry, we need to understand how gloss is perceived. So typically, when we have a glossy surface, like in this case, we see the bottom left sample there is a very glossy black surface. As we have light coming in from one side, it hits that surface and then it gets reflected back in the opposite direction of where it initially comes from, towards an observer. And typically on a glossy surface or a very high gloss surface, we'll get a very clear reflected image of whatever that light source is. So in this case, you can see this crosshair. And that would be an example of how clear that reflected image is. Now, when we have a matte surface, what's happening there is there's microtextures on the top of that surface, so it's not perfectly smooth, which causes scattering of light. So as the light comes down and hits that surface, it gets reflected back towards the observer. But now, because of that added microtexture, we see that the light is not all going to that observer. It's now getting scattered around, with still a majority going back to the observer. So that's essentially what the difference is between a high gloss and a low gloss surface, and how that light's being reflected. So why did we go over that? We went over that because glossy, your gloss on your products, your gloss on your surfaces, that's going to play a role into our visual interpretation or visual impression. So gloss and color go hand in hand. And you can see here with these samples here, these are exactly the same colors. So we have a glossy matte sample, we have a glossy black sample, we have a matte black sample, and then next to that we have a glossy red sample and a matte red sample. With those two colors, both sides of them are exactly the same color. The only difference is that surface. We have the glossy side and we have the matte side. The glossy part looks darker, more saturated, but it's the same exact pigmentation being used. So we see that color and gloss combined in order to influence that end visual impression. So how is color perceived? So typically in a 45-0 setup, this is what you would see. So we have a light source that comes in from 45 degrees. That specular gloss, or that specular reflection, gets reflected back towards a gloss sensor, while there's an observer directly overhead that's going to be measuring that color. And the reason we have this setup is because, think of like a magazine. If you're reading a magazine, they're typically very glossy. You don't want to read it to where that white light or that gloss is shining directly into your eyes. You want to read it to where you can read the words and avoid that specular reflection. So this is typically a 45-0 geometry setup. This is that same setup, but on a matte surface. So you see some of that light will get scattered into the observer, but for the most part, it will just be measuring that color directly overhead. And this can also be switched. So an example of that would be if the observer was where the sun was and the sun was where the observer was. So in that case, it would be your light source at 0 degrees and then your observer at 45 degrees. So each one creates the same conditions. All right. So as I mentioned before, there's two different geometries with the Spectra 2 guide. There's the 45-0, which is measuring color as we see it. So this is going to be our best representation for what our eyes are actually seeing. We see basically how it works. Just like this example on the right side there of the person looking down, we have a light source coming in from 45 degrees. In the case of the Spectra 2 guide, it's circumferential light, meaning that there's light coming from all directions. That's nice because you can orient the instrument in any type of way, and it's still going to get the same result every time that you measure it on a surface. If you have light just coming from a single direction, depending on how that material is made or what type of pigments are in it, you may get a different result depending on how you orient that instrument on the surface. But in this case, we have circumferential light, so coming from all sides. We have the light source coming in from 45 degrees, and then directly overhead is that detector, which is going to give us our color. And we find that with this instrument and the specific geometry being 45-0, differences in gloss and structure on that surface are going to equal color differences. So just like how we saw those initial samples with that black glossy side and the black matte side, those differences in structure or in gloss, we can clearly see those differences. So this instrument will give you exactly what we're seeing. All right, we see typical applications is comparison to a defined standard. So if you're doing sample to standard comparisons, good for batch to batch controls. So for quality controlling your color, typically on products being sold to consumers. See it also, it's good for harmonization of various materials and structures. So if we want everything to match its end appearance, this is the instrument to use. And you see again, circumferential illumination reduces that directionality influence. So if you just have, say, some special type of material, depending on how it was made, if you shine a light in one direction, it'll look one way, but if you shine a light on a horizontal or vertical direction, it might look a different way. All right. So our other instrument is the D8. And with that instrument, you can choose to have a spin, which means specular included, or a specs, which means specular excluded. Basically what that means, as you can see here on this image, we have a sphere, so a completely white sphere, and we have a light that comes in from the side. So initially with the 45-0, we use direct light, but with the sphere instrument, we're using diffused light. So there's no direct light hitting that surface. So essentially what we have is a light coming in from the side that then gets reflected along the white coating of that internal sphere until it eventually hits that sample. And in this case, since we have the spin mode, which is specular included, it's including the gloss of that surface in the total color measurement. So there's no separation between gloss and your color. It's being included in there. And so what you'll find with this type of geometry and setup is that you're only going to be able to match pigmentation, and it's not going to take into account that structure and that gloss. So we see typical applications as for color matching, like pigment matching, color strength development, and weathering studies. Because in weathering studies, we don't care about what the surface, what that surface structure is. We're trying to find out if that pigmentation is slowly, weathering. So with this setup here, a sphere with specular included mode, we see that a difference in gloss and structure does not equal color differences. So if you remember back to that original example with that glossy side and the matte side, this instrument setup will tell you that both of those sides are exactly the same pigmentation because it's not taking into account that gloss and structure. All right. So our other option that we have is specs. So if we're using a sphere instrument, there's another mode on it called specular excluded. And what this does is it now has a gloss trap to measure that gloss. So if we have gloss coming in off that surface, it'll be put into its own measurement category. And what we find with this instrument is that it has a high correlation to 45-0, but only on high gloss surfaces. As you get lower gloss levels, your correlation to your 45-0 diminishes. And the reason for that is because the gloss trap does not capture all the diffuse light from the specular reflection. So it's not capturing everything. It's just capturing what it can. So with this instrument setup, with the sphere and specular excluded mode, you have a difference in gloss structure will equal color differences. However, it will not be exactly how our eyes see, and it won't be directly comparable to a 45-0 instrument. So here's some studies that were done between all three types. And we see the samples up here in the top right corner. So we see that black glossy side and that black matte side. So starting with our 45-0 instrument, we see that on the glossy side, which is the blue line here, we see that it's pretty comparable to the D8 specs geometry. It's almost the same with your L value, your A value, and your B value. There's some slight differences, but for the most part, it's pretty close to the same. However, when we look at our D8 spin instrument, see that the values for that glossy side are very, very off. And then when we go and look at the matte surface, if you remember from the previous slide, as you get lower in gloss level, your correlation between the 45-0 and the specular excluded slowly diminishes. We see that here. So with our L value on that orange bar, so that matte side, we see that the L value is somewhere around 23, whereas on the specs instrument, it's around, let's say, 27 or 28. So it's a fairly decent difference in color that it's measuring, and that's due to the low level. So we see that in some cases we can get a good correlation between the two, but in other cases we don't. And then when we look at our D8 spin instrument, because it's measuring that true color, not taking into account that surface, we see that it's measuring both the glossy and the matte surface almost as the same values. So that's a great study for that. And then here we have another one, but this is now with a colored sample, with that original red sample. And so we see if we look at the red glossy side and we compare the 45-0 to the D8 specs, we see that those blue lines, the blue graph is almost spot on, right? It's very close to the same. But if we look at the orange sides, the matte surface, we see that now the correlation is slowly going away. And that's because we're no longer looking at that high glossy surface. So we see, for example, on the L value for the 45-0 and the red matte sample, we see that's around 40 versus the D8 specs. We see that's probably somewhere around 42. So it starts to vary. And then when we look at the D8 spin geometry, we see that it measures both of those sides of that sample exactly the same because it's just measuring that true color. So now switching gears, with our Spectra 2 guide instrument, we have a Pro model that can answer this question we have here on the slide, which is how can we describe black? So with black measurement, we're trying to measure the complete absence of color. And so when you have the complete absence of color and you have these deep jet blacks that a lot of industries are moving towards, you have trouble measuring and being able to accurately depict what those values are. So the question gets raised, are LAB values suitable to describe black? If you're unfamiliar with LAB values, essentially, those are your color coordinates that are widely accepted worldwide, describing color. So we see that when we measure these deep blacks with typical LAB values in standard settings, we see that those reflectance curves, so the specular reflectance curves, are so low because there's almost no reflection coming back to the sensor. So we have that trouble measuring those deep blacks. So to answer the question, are LAB values suitable to describe black? Yes and no. So as you get down to the very deep blacks, you need to come up with a new type of scaling system. So this was one of the scaling systems that we developed. The special indices for describing jet blacks. In this, we have 3 different values. So we have an MY value, which is our hue independent black value. So this it best describes the blackness of that sample, independent from the hue or the undertone of that black. We also have the blackness MC value, which is your degree of blackness that is dependent on the colored undertone. Typically, you'll find that with deep blacks and those jet black colors, you'll have an undertone of either blue or dark brown. Typically, the dark blue undertone gives it that deeper jetter look. And then lastly, we have our undertone DM value. And so that's our absolute contribution of that hue or that undertone in the black color. And we see this is the calculation for that. And with this, these special indices, we can then describe very deep black colors. However, when you start describing and measuring these very deep black colors, you inevitably end up getting into this wall, or hitting this wall, and that is electrical noise. So if you're unfamiliar, almost every electronic has some sort of electrical noise associated with it. In some cases, it's very low, so it's not really detectable. But as you start getting these very, very low reflectance values, in this case, we see this full spectral curve of a black color that's almost at 0. You start getting interference with the internal electrical noise of the instrument. So in order to combat this, we have a new Spectra 2 Guide Pro, which has special calibration procedures and process, an adapted production process, special precision electronic and optical components, and all these come together to reduce the noise that the instrument is having, which can then get you more accurate results. And we see that there's also an amplified signal, so we used LEDs that are powered with more energy and a higher light intensity. There's also an extended illumination time. So all of this is put together in a special mode that we call jetness mode. And this is for specifically measuring those deep blacks, which is important because a lot of industries are starting to move towards these jet blacks just because of their appearance. To the consumer, it's very cool looking. It's not a color you see all the time. And because of its complete lack of reflectance, it has this very unique look when applied to certain products. And so this is a study that was done with our Spectra 2 Guide Pros under that jetness mode. So we see this as an example of a sample that was measured 50 times in immediate succession in the same spot. From looking at the graph, it looks a bit jumpy there. However, if you look at the values, it's only a standard deviation of 0.0002. So that's a very low value, meaning that this instrument has a very high repeatability, which is great, or very low repeatability. All right, and just reiterating the advanced mechanics of the Spectra 2 Guide Pro. So we had the adapted production process. In it, we used higher precision electronics, optical components. We developed our own special calibration routine. So it was a little bit different than the other models. The temperature stability test was done on a dark gray instead of a white to improve that jetness mode. And then we see we used LEDs that were powered with more energy, so the light was brighter, and it stayed on for a longer time. So we were able to capture more data with that extended illumination time in order to accurately depict the differences between very jet black colors. So we have a very good improved accuracy on dark colors. And we partnered with a company called Orion, who engineers these special deep carbon black pigments. So they made this instrument possible with their help and their materials. All right, so switching from handheld solid colors and jetness measurement, we're going to move into some effect coatings and some instruments that we have for that. But to start off with effect coatings, 80% of today's automotive finishes are effect coatings. What that means is that they have some type of metallic and sparkle effects. So we see metallic coatings, sometimes have the light dark flap. And what this is, you can see this on this car. But as you move up and down the car with the different viewing angles, you'll see spots that go from very light to very dark, depending on the contours of the vehicle. That's called a light dark flap. And then we see further down a pearlescent coating, which has an effect called a color flap, which means from one angle it looks like a different color, in this case green. And as you move along that car body, depending on the illumination angle and the viewing angle, it'll turn into a completely different color. So if you've ever seen one of these on the road, you'll know exactly what it is, but it's a very interesting effect going on. And then lastly, you want to be able to measure special finishes like glitter effects, just certain types of metallic flake, and be able to characterize them. So to understand what's happening when these measurements are taking place, this is an example of a solid green color, and the graph is the spectral reflectance curve. You can think of that like the fingerprint of a color. So in this case, when we measure it from all the angles, that color, or that fingerprint of the color, is essentially remaining the same across all those angles. It does vary slightly, but for the most part, it's pretty consistent. And that's what you'll find in a solid color, because as you take the color or that tile, that green tile, and you move it around into different angles, you're still seeing the same color. It's not changing darkness. However, when you have a metallic green, we start to see these big differences in that spectral reflectance curve. So in this case, we see that at the 110 angle, we have it very low. So we can say this is an obvious light dark flop. So on the 110 degree angle, it's a very low reflectance value. So it's almost like a dark black color. And as we take measurements at the different angles, we see that it slowly starts rising up. And at 15 degrees, it's a very light green. So what we're seeing is that with this multi-angle instrument, we find that all the angles are producing different colors. So this is important when you're trying to analyze those metallic colors, because they have special properties that we otherwise wouldn't see if we didn't measure all the angles. One of the most notorious colors for this light dark flop are metallic silvers. So what you'll see here in this reflectance graph is that at 110 degrees and at 75 degrees, it's almost pitch black, so it's really dark. And then at the low angles of 15 degrees, we see that it's a very light color. So it goes from almost a very dark color to a very light color, with silver in the middle. And so this is specifically designed for a lot of car manufacturers that put nice contours in their vehicles. It's supposed to bring out this effect, bring out this look, and really make the car look more pleasing to the eye. So this is our instrument here that's able to measure those different angles for specifically metallic and effect coatings. So we have our Bic Mac eye, and it does not only multi-angle color analysis, but it also does flake characterization. So how that you can determine how that flake is laying, how bright the flake is, how shiny it is, what the sparkle content's like. So we see the MAC in the Bic Mac stands for multi-angle colorimeter. So that's a nice little bit of information. But we see that it illuminates at 45 degrees, and then it has detection angles at 6 angles, starting with -15, and then it goes to 15 degrees, 25 degrees, 45 degrees, 75, and 110 degrees. So we have 6 different angles to choose from. Then we have a sparkle characterization. So what this is it uses direct light to illuminate the surface at 15 degrees, 75 degrees, and 45 degrees. And what's nice about that is that you can find out if all your flake is laying flat, just by looking at the different angles under that direct illumination. So if you see that, you have a high sparkle intensity, or high sparkle content at 15 degrees, and you have no sparkle at all in 75 or 45, then you can say that all your flake is laying perfectly flat. However, you can also find out what's going on in the process by using those angles and analyzing that data. We see that there's also a camera that detects that sparkle at 0 degrees. And then lastly, we have a graininess characterization. So if you ever look at a vehicle in direct light, you'll see sparkles, and then under, say, an overcast day, you'll see graininess. So what that is it's just essentially, using diffused illumination, and you're able to find out how much grain is in that coating. And so this Bic Mac eye can also measure that graininess characterization. So that's it for today, folks. So I'll hand it back over to John.
All right. Thanks, Noah. So that's what the MAC and Bic Mac stands for. Taught me something new today. So thank you for that. Multi-angle colorimeter. Like I said, if anyone has any questions, please log them in the chat box. Should be in the bottom right-hand corner of your screen, and we'll get to them. Got plenty of time here. I'm just going to get right into the questions here. We got a few. Do you have equipment to measure color in wet layer before curing?
So we have special types of sample holders to where you can do, drawdowns of, say, a wet coating and then measure that wet coating. But with that, it would be, either the Spectro 2 guide or the Bic Mac. So if you're measuring either solid color or metallic color or effect color, you would use those 2 instruments, but with a special apparatus to hold the sample.
Yep. We have lots of those little attachments for, specialty uses. Another question here. Sphere spin, is that a true color measurement?
Yes. So that'll measure, pigmentation. So it's not going to take into account any surface quality. It's just going to strictly look at that true color.
Yep. Good. Maybe just touch again, difference between spin and specs.
Yeah, absolutely. Let me pull up that slide. So with spin, so if you look at a sphere instrument under spin, which is specular included, it's not differentiating that gloss. So all that value, or that traditional gloss value, is still being accounted for in this color measurement.
Mhm.
So what you'll find is a difference in gloss and structure. So if you have a matte versus glossy surface, but they're the same pigmentation that's used, then it will only look at that pigmentation and won't take into account any surface qualities.
Mhm.
Whereas the sphere specs or specular excluded, it has that gloss trap, so it's not taken into the gloss reflectance as your values, and with that, it a difference in that gloss and structure are going to make color differences. So it's kind of a way where you can use the sphere geometry and still get data that can somewhat correlate to what we can visually see.
Yeah.
But in most cases, or not in most cases, but in some cases, it may not be as accurate, but it's close.
Okay. Okay. I think a related question here. Can you review why, again, the geometry of diffuse light and 8-degree observer angle with specular reflectance included is used with weathering testing, color retention versus exclusion?
Yes,
Okay.
because when you are weathering a sample, so I'll pull up a sample here. So we can assume in this case, this glossy surface would be before weathering, and this matte surface would be after weathering. As you weather material, the surface can get weathered and change its appearance. Usually, it gets more matte as it gets weathered. So in this case, in order to measure that true color to see if that pigmentation is also degrading, we would use that specular included instrument, because we don't care about what that surface structure is doing. We just strictly want to look at what that pigmentation is doing, and that sphere specular included instrument is able to take all that information, not account for that surface, but just look at that pigmentation value.
Mm-hmm.
Does that answer your question?
Yeah, I think so. Yeah, if you need us to elaborate, just log it in the chat and we'll continue, or Noah will. He's the technical expert here. Carmen asks, how can we measure liquid color?
Great question.
Yeah.
So liquid color, you can do it with some of our other instruments. For example, our Color 2 View. You can purchase a special sample holder that you can put liquid in and then measure that. But typically, it's done in a different fashion just because of the implications you can have. You can't really just put the Spectrum 2 guide over top of a liquid and measure. There are special standards that you have to follow when doing that. But I would urge you to get into contact with one of us, and we can certainly walk through any type of application you have and see what instrument would really work best with your material.
Yeah, that's a great reminder. Yeah, any questions you have? Yeah, thank you, Noah. There's Noah's email address. He's one of our technical experts. We also have field representatives around the country, technical folks that can travel around. You can hit reply to any of the marketing messages. It'll come to my team and we'll route it to the appropriate person. But yeah, we can take in samples. You can have discussions, and based on your specific need, your process, we can make recommendations to streamline that, to make sure you're getting accurate data in your process. So yeah, great stuff. Next question here: are the substrates affected by gloss measurement?
So yes and no, it certainly could affect it. But in most cases, when you're measuring the gloss, or in any type of gloss measurement, it's just strictly looking at that coating. So there are some circumstances where it could affect it, but in most cases, no.
So for the most part, your color measurement and your gloss measurement are two separate things. Yes.
Yes.
Yep. And, I don't know if you touched on this. If you're producing something with a fluorescent, our Spectra 2 guide also has a built-in fluorimeter. So that can also help with weathering aspects.
Yeah, it's a great thing to add. So it has the capability of measuring that fluorescence, but something cool is that with the software, you can see what that color would look like or how much it would differ from the standard when it has zero fluorescence in it. Because eventually fluorescence is one of those things where it's there for a certain amount of time, but it can degrade over time, and eventually that color will lose all of its fluorescent properties. So if you have a vehicle that's fluorescent, slowly that sun will damage that fluorescence, and over time your vehicle will lose all of that fluorescence, and then you'll have a different color. It won't look the same.
Yep, exactly. Next question. Love all these questions, folks. Keep them coming. Do you recommend to have both types of equipment, the 45-0 and the sphere, for injection molding applications?
That's a great question. It really depends on what you're looking for, but I can see, certain situations where it'd be good to have, one of each, a D8 sphere instrument. I could see where it's good to have that if you're just looking for the pigmentation, just to make sure that your colors are all the same. And then I could see where it's good to have the 45-0 just to be able to match, batch to batch control.
Yep. Excellent. Let's see, what do we got here next? What is your recommended equipment for measuring daylight reflectance of yellow thermoplastics used for traffic markings?
That's a good question.
I haven't heard that one before.
Yeah, I'd love to see the type of samples that you're referring to. I think it could be done with the Spectra 2 guide, but I'd love to see what type of samples you have, and maybe there's another instrument that would work better for that situation.
Yeah, Nelson. Well, thanks for the question. We'll get in touch with you. We'd love to, take some samples, run some tests, if you don't mind. That would be great. Let's see. Carrying on here. Do you have best practices for measuring a two-tone sample? Example, a base coat and a top coat are both visible but are different colors. Two different browns, for example.
So, interesting question. So do you mean by that is the base coat and the top coat are on top of each other, or are they next to each other when you say they're both visible?
Yeah. Paige, I've unlocked your microphone. If you want to chime in and elaborate on your question, you can unmute yourself in the upper right-hand corner. There's a kind of a red circle with a microphone in it. If you're able to unmute yourself, we'd love to hear your voice. I get sick of hearing myself and Noah.
Can you hear me?
Yes. Hi, Paige. Welcome.
Yeah. Hi. Yeah, so they're like stacked colors. So basically it's like a base coat and then top coat on top, but the top coat isn't covering the base coat entirely.
Okay. I guess, well, in that case, you could, I would use like a 45-0 instrument and take a measurement over that top coat and then take a measurement over that base coat. And then you can see measure those different colors, according to how you'd like to.
Does that make sense?
Yeah. Is there any way to do it once they've already been like cured?
Do you mean like if the top coat was cured over top of the base coat?
Yeah.
You wouldn't be able to measure them separately. So you in that case you just have to measure the surface. And that would be whatever color that top coat would be. unless it's very very transparent and you can see that base coat underneath of it. Essentially, what it will do is it'll just measure what you're seeing on that surface.
Okay.
Does that help?
Yeah. Thanks.
Kind of.
Kind of.
Kind of. Take a look. Email more Noah, and he can set up a separate time and work through that with you.
All right.
You know, whether it's sending in samples and him running tests. Don't mind me volunteering your time, Morgan, or don't Noah there. Okay, let's see. Back on track. Can you measure color in the specular direction? Some materials, bottles solid state colors show color in specular reflection.
So
you got that?
Yep. So in that case, you have to really look at the geometries that the instrument's using. So a 45-0 instrument is going to read directly overhead of the sample, whereas if you have a multi-angle instrument, it's going to read at those several different angles. So pull that up. So you have the -15, the 15 degrees, the 25 degrees, 45, 75, 110. So somewhere within there, you could be able to, find out where that specular angle is and measure that specular angle. But for the most part, it's not typically done. And that's because that specular direction, that's where it's usually that white light that's coming through. So specular reflectance is that gloss value. So it's typically that white light. So if you were to put a detector there, typically all it will capture is that white light being reflected off the surface.
Excellent. Okay, what's next? We use a polyura type paint, but the texture really affects the visual appearance. But the color measurement on the tool is not that different. Why?
So in that case, if you see a big difference with the surface,
Yeah.
In this case, the texture is affecting it. So you're most likely using a specular included sphere instrument. And what that's doing is not taking into account that surface, but it's just looking at the pigmentation. So in your case, it's most likely saying that the pigmentation between what you measured and what you're trying to achieve is spot on or very close. But that surface texture that's not being taken into account with that instrument is what's causing that visual difference.
Yeah. And does gloss play a part in that too? What you're seeing versus, the color measurement number only unless you're also getting that gloss value.
Yeah. So of course, think of low gloss surfaces just having a lot of texture, right? Whereas high gloss surfaces are very smooth. And as you get in that low gloss with that texture, it's scattering the light in different directions, and that's what's giving you that main difference. Pull up this example again. It's a great example. But that matte surface looks a lot different than the glossy surface, and that's only because of the micro texture that's in that matte surface. It's causing the light to scatter in different directions, so we're not going to see that smooth finish and that bright white light, which is the gloss, clearly.
Yeah, no, that makes sense. So is there a best practice to both get the color and the gloss values and measure that throughout against your sample versus what's coming off the production lines? If that's important to what you're doing, in terms of your application.
Yeah, so it all depends on what you're looking for. If you're looking to match pigments, to make sure that, say, a supplier is supplying the right pigment, or if you're looking for that end appearance, right? If you're trying to make sure that all your material is going to match that glossy black sample, if that's your end appearance, you're trying to match that. You would want an instrument that measures just like how our eyes see, which is the 45-0.
Okay.
Because if you start measuring samples and you start to see that they're getting visually less glossy, that instrument will be able to detect that, and then you'll be able to see that data numerically. So all of that 45-0 is doing is it's putting numbers to what we're visually seeing.
Mm-hmm.
Whereas your specular included instrument, all that's doing is it's not taking into account what that surface looks like, but it's only looking at that strict, true pigmentation or color. Mm-hmm. So you could have, obviously gloss plays a role in what that end appearance is. So you're looking to match your products all to one physical appearance. You want to use a 45-0 instrument for that.
Gotcha. Thanks for going into a little more detail on that. Question here. Can you measure color in retroreflection?
Retroreflection. I have to be honest here. I'm not familiar with retroreflection, but I can do some research into that. Or if you want to explain a little more.
Yeah. Dirk, I unlocked your microphone. If you want to chime in, you're more than welcome to. There's an unmute button in the upper right-hand corner. It should be a red circle with a microphone in it. If you click that, you'll be live. Feel like a radio show. But if you're able to, go for it. We'll keep moving here. We'll get back in touch with you, after the fact here. Let's see. Can the Bic Mac eye detect particle shape and size during characterization?
Great question. So when it does that characterization, usually when it's for sparkle, it's not exactly detecting the shape and size, but instead it's looking at how intense the sample area and how intense those sparkles are. So the light intensity of all those sparkles combined. And it's also going to look at the area within that measurement area that's emitting the sparkle light. So that's how it's going to detect your differences. So it's going to look at sparkle area and sparkle intensity. And you can, look at the different angles that it's measuring in and determine, in some cases you might have more sparkle intensity at a certain angle. And that could tell you that your flake is laying in a certain orientation. And then you can compare that with the other angles and see, there might be a few outliers. So there's a little bit of sparkle intensity at some other angles. Mm-hmm. And the same is done with graininess measurement, except in graininess measurement, it's using diffused light instead of that direct light.
Nice. Cool stuff. We'll just keep rolling. Oh, and a quick shout out to our new regional sales manager out on the West Coast, Charles. Welcome. I've chatted with him a little bit and he's absorbing it and following along and learning. So thank you, Noah, for sharing your expertise and spreading the color measurement love.
Anytime.
You bet. Okay, next question here. How do we correlate measurements from BIC with other companies? Or does all equipment from different manufacturers have the same or similar readings?
That's a great question. So, whenever you're measuring with instrumentation, right, and it's from different manufacturers, you never want to rely on just the absolute data. So just, the absolute values. You only want to measure in difference mode. So that means your comparison between a known standard and your sample. And that's because if an instrument, may use a different light source, or it may not be as high of a grade as a light source, so it's not perfect. Yeah. Every manufacturer uses different materials, so they may not read perfect and exactly the same with absolute mode, but you should get very, very close results, if not spot on, with your difference measurements. Meaning, if you have an instrument from one manufacturer and it's going to measure your standard, and then you go to measure your sample, your delta E or whatever delta equation you're using, or your difference equation, will give you a very close result as if you're using another manufacturer equipment, because it's just using that data that it creates internally and then comparing it against itself. So that difference data should be exactly the same, or if not very close. But absolute data, you may see differences in that.
Nice. This is back, well, let's see. What would you recommend for harmony, the 45-0 or the sphere, and why?
For harmony, I would recommend the 45-0,
Okay.
because you're typically going to be looking at how everything comes together, and that includes both the full visual impression, so the color and the gloss. You're not just looking at the pigmentation in that case. You're looking at the entire visual impression and making sure all the parts that are coming together look exactly the same and are harmonizing with each other.
Yep. Good. Sparkle angles. So now talking about the Big Mac multi-angle, what sparkle angles are most important in the paint process?
Yes, great question. Pull up that slide here. So typically, it measures in 3 different angles of 15, 45, and 75.
Yeah.
And typically the 75-degree angle, I want to say, is usually the most important, because you can see, or no, the 45-degree angle is most important because you can see how that sparkles is laying on that surface. I think I mentioned before a couple of times, but you're looking for that difference in that sparkle intensity and the sparkle area to see where that sparkle is lying, if it's lying flat or if all that flake is in different directions and giving you different sparkle appearances.
Yeah.
So typically that 45-0 or that 45-degree is the best angle for that.
Okay, good. Now, is there a certain sparkle angle that would show a, or I guess would display a formulation issue? I'm not saying that right.
I want to say the 15-degree angle.
Yeah.
It's somewhat valuable for displaying that, because if you see here in this image at that 15-degree sparkle illumination, you can see that's where you'll find if your sparkle is the same size or not. That's where you can see the difference in sparkle area.
Yeah.
And characterize, that, say, at 15 degrees, that sparkle will look, a lot. It'll cover a lot more area compared to, say, if you looked at it from 45 degrees or 75 degrees, and then you can identify if there's an issue within the formulation of the paint that could be causing, the differences in sparkle.
Yeah. Okay, so 15 degree is basically your formulation angle. Would the 75-degree be your process angle?
Correct, because that's looking at how the flake is laying.
Look at me go. Score 1 for marketing, huh? How about that?
Excellent.
Yeah, I always learn stuff from you here. Question here from Gary. Do you have a preference for delta E equation?
Yes. So, if you're going to be using delta E for solid color, you really want to look at the newest, which would be the latest and greatest color equation, and that is delta E 2000. So that equation takes into account a lot of different studies that were done, and it creates tolerances based off of how our eyes perceive color. If you really think about it, the delta E star equation that was developed back in the 60s. And since then, there's been a lot more technological development. And then so now the latest and greatest equation for solid color, I would say, is delta E 2000.
Cool. Thank you. A couple more questions here. Can you clarify digital standards and how they can help improve color harmony?
Can you say that question one more time?
Yeah. Can you clarify digital standards
Yes.
and how they can help improve color harmony?
Yes, I can. So, with our instruments, they all work with a software called Smart Chart, and the software is very nice because you have the ability to, take measurements for standards, and then you can share them via email with different suppliers, different plants, so that traditionally, when you had a standard you're trying to reach, you would send out a tile or a standard plaque, and then the problems you have with that is that those tiles and those standard plaques aren't always exactly the same. There could be small differences,
Mm-hmm.
and that creates a problem because if one plant is using, one tile and another plant is using another tile, and say both of these tiles are slightly different, and then you have further down the line, you have some products that are being measured. And those products are at the very end of the tolerances for each of those tiles, those standard tiles. Then your end product, when those parts come together, they could be a little bit different. You'll be able to see those differences. Versus if you had digital standards, it's just one, you take a measurement for one standard tile. You don't have to send it anywhere, so there's no risk of it getting lost or scratched. You just use that digital data, which is that full spectral reflectance curve of the standard. And then you can compare directly to that. So your tolerancing is always going to be exactly the same. Your standard is pinpointed. It's exactly the same for all your plants. So it's a great advantage that we're able to come up with different technology.
No, excellent. Okay, last question here. We have a few minutes. This is a great question. Can these color measuring instruments be used for automatic checks on assembly lines? For example, colors like white and pearl white, cameras used for quality checks struggle to differentiate between the two, but it'd also be great for these measuring instruments somehow integrated with a PLC on the line.
Yeah, absolutely.
Robotics,
So we have our robotic instruments that work. They can go on cobots or different types of robotic arms, and these instruments are designed to be able to work autonomously, and then connect to those PLC those servers and put all your data up and organize it perfectly. So it's a great system. If you're interested in one of those, I would definitely recommend reaching out. And we can do some demos for you as well.
Yep, absolutely. And I did in the chat just put a link. We have a YouTube channel that has a playlist that's just dedicated to some robotic videos that show some of our wave scan or Bic Mac in action there. So check that out. Just look for that playlist, and you can look there. Definitely reach out, like Noah said, and we can chat more and see what types of applications and types of things you're running and see how we can best integrate it. Also, I just threw in here in the chat again a link to our technical articles. In our knowledge library on the website, bic-instruments.com, or just copy that link. Lots of articles, more in the technical nature. So if you want to dive deeper into any of these topics that Noah mentioned, it's all there. Just take a look. And, as always, reach out to us if we can help in any way. Any final words from you, Noah?
It's a lot of technology has been developed, for being able to put numbers to what we're visually seeing. And I urge you, if you have some type of manufacturing or if you're looking for some type of color control, to reach out to, me or anybody at the company.
Yep.
And we'd be happy to talk through some solutions that we could provide for you.
Yeah, that's a good point, because really everyone in the field and everyone back at the office, Noah included, we like to understand your process, and we can recommend how to improve those processes, reduce scrap, waste, and make sure your data is correlating between shift 1 and shift 2, or between plant 1, 2, and 3. Lots of different variables, but we can really review your entire color program and recommend some, optimizations for that. So with that, like I said, you'll be getting a copy of this in your email. Feel free to share it with colleagues. Reach back, hit reply if you have any questions at all from us. We appreciate all the great questions. Other than the traffic color one, I think that's the only one that kind of stumped the Noah. So we can play again next month, and we'll see what we can do. But on that traffic, we'll reach out to you independently and get some samples and run some tests there. So with that, thank you for attending. Thank you for joining us today. Hope you learned something. Noah always teaches me, and we just look forward to seeing you on future webinars by Bit Gardener. So thank you, and have a great rest of your day.
Thank you.